Great, Charles. Welcome to Trigonometric Integration Part 2. Just before we start with Part 2, I just want to quickly let you guys know I made a mistake in Trigonometric Integration Part 1. So example on page 83, when I did the integration of example number 2, you'll see that I said the sine of x over 2 is sine of x over 2. It should in fact be cos of x over 2. So if you were taking notes, please just go back to that one and fix it. I'm sure you probably already picked it up in the previous video. It's a pity you guys aren't here to just stop me and go, ma'am, you wrote it wrong. But anyway, right, so please go and fix that for me. Right. Now, we're continuing with this trigonometric integration, and as I said, we did first our standard integral. So the standard integrals is based on that table of derivatives. And then we spent quite a bit of time talking about how we can use the identities to then also do trigonometric integration. So the whole idea with identity is the original integral is not one of my standard integrals, but using the trigonometric identities, I then change it into something that is a standard integral, where I can then go and I can use my table of derivatives. Okay, another one of the identities I can use are my square identities. So I've got these two square identities, believe it or not, that you might not be very familiar with because we don't use them in core mathematics at all. But they are on the information booklet. So on the information booklet, you've got your standard one, which you should know. Sine squared a plus cos squared a is 1. And then we have these two for tan squared a and for cot squared a. Okay. Now, again, unfortunately, we are not going to use them as is. We're going to have to manipulate them slightly in order to use them in trig integration. So this one, pretty easy manipulation. We're just going to state that tan squared a is then going to be equal to sec squared a minus 1. And this little one right there, we're also going to go and say cot squared a is then going to be cosec squared a minus 1. So these are the variations that we're going to use. But like I said, they're not available on your information booklet. You have to know to manipulate them in order to use them. So if I then go to these two examples on page 84, the first one, it says the integral of tan squared x dx. So I can use this identity right there, like this. This identity right there I can then use, and I can say this is then going to be the integral of sec squared a, sec squared x in this case, minus 1. So we put a bracket around it, we write the dx. I did mention in the previous video, watch that notation, don't forget to write dx, otherwise you will get penalized. Okay. Now, the reason this was so useful is because tan squared x, if you did look it up on your table of derivatives, you realize there's no tan squared x anywhere there on the right hand side, so it is not a standard integral. But the moment we changed it to sec squared x, if you look at that table now, you realize that sec squared x is a standard integral. So if I find the integral of sec squared x, it's going to be tan of x. So I can change this then by saying the integral of sec squared x is then tan of x, and the integral of negative 1 is then minus x, and then plus c, and I'm done. Very simple and straightforward if you use the correct identity. And then exactly the same principle over here, we can say this is then going to be the integral based on what we did over there. Cot squared a is cosec squared a minus 1. So cot squared x is then equal to cosec squared x minus 1 dx. Put the bracket around and don't forget the dx. Please, please, please don't forget it. So now, if I look at my table of derivatives on the right hand side, I spot over there cosec squared x, and I transfer the minus, is then going to be equal to minus cot of x if I find the integral. So this is then going to be minus cot of x minus x plus c. So there I can use my square identities in order to change these, so I can then go and I can do the integrals. Great. Now the next identities are the compound angle identities, but you will not recognize them in this form at all. You can actually go and you can check whether this works or not, meaning you could go and write this out, this part, and then you can go and you can expand your compound angle identities, and if you expand your compound angle identities and multiply by half, you will get to this. Good news, however, this is the only one of these trig identities we're going to use, which we do not have to manipulate. It's already in the correct form. So here at least they knew it would take you forever if you had to manipulate it. So they've given these identities to you at the bottom of page 2, right over here. So at the bottom of page 2, it gives you that if you have sine of an angle, cos of a different angle. So this one is not like when I was using my double angle for sine, because for my double angle for sine, these angles need to be the same. So if these angles are different, then I can go and I can say it's half the sine of the angle of the first angle, in this case the angle in the sine function, plus the second angle, plus the sine of the first angle minus the second angle, and so forth. You can actually just go and you can look at them and they work as substitutions. The first one works with sine of an angle, cos of a different angle. The second one works with sine of an angle, sine of a different angle. And the last one is cos of an angle, cos of a different angle. So those ones are available. We'll recognize them quite easily because in the example, they will multiply the sine function with a cosine function, or sine function with sine function, or cosine function with cosine function, but very important, the angles are not the same. So what we can do then is this one's got sine of an angle, cos of an angle, which then refers to this one over here. So it's the half, and we can always write the half in front because that's a constant multiple. And then we say it's sine of the first angle plus the second angle, so 3x plus x. So it's going to be sine of 4x. Plus then the sine of the first angle minus the second angle. Now careful, that first angle has got to be the angle with a sine function. So that means this one's going to be the sine of 3x minus x, which is then going to be the sine of 2x. And I put the bracket around, and I put the dx. And then this is also very easy to integrate. And the reason it's easy to integrate if I bring the half down is because these are standard integrals. They're on my table of derivatives. So I know that if I want to integrate, sine x becomes negative cos x. So this is then going to be negative cos of 4x, and please remember with that reverse chain rule, just divide by the 4. And I want to remind you again, we can only use this little shortcut if the inside function's derivative is a constant, then I divide by that 4. This one exactly the same thing, it's minus cos of 2x divided by 2. And then I put the plus c down. So I'm just going to clean this up by multiplying by a half. So this is going to be minus cos of 4x over 8 minus cos of 2x over 4 plus c. And then we can do another one of these. This one is an exercise 3.1 on page 84. So this one has a constant value there, it's got a 4. So if it's got that constant value, I can then just go and say it's a constant multiple. I can then move it to the front. Careful, it's not a constant addition that you can move to the front. It's always a constant multiple that you can move to the front of an integral. So don't get that confused. So I can move the 4 to the front, and then I can go and I can say, because it's the cos of an angle, cos of a different angle, I have to use this version of that formula. So I've got the half here, which means I will put the half over there, and I will multiply it by the 4 on the outside. And then I will go and say, it's cos of the first angle minus the second angle. So it's cos of 3x minus 2x, which is x. And then it's plus cos. And this one is going to be the first angle plus the second angle. So 3x plus 2x, which is 5x. Simple, easy, and straightforward. We can then go and say half times 4 is going to be 2. This is then going to be one of my standard integrals. If I look at my table of derivatives, the integral of cos x is sine x. So that's just going to be sine x, and there's not really, well, the inside function, the derivative of the inside function is 1, so you can divide by 1, but it's really not necessary. And then this one is going to be plus sine of 5x over 5. And then I can put the plus c down, and I can clean it up by multiplying by 2. So this is going to be 2 sine x plus 2 sine 5x over 5 plus c. There you go. Okay, so pretty easy to use, and like I said, it's on your formula sheet. You just have to recognize when it's necessary to go to these formulas so that you can use them. Okay, next. Now, next what we have to look at is we have to look at using the reverse chain rule, but specifically the more complicated versions of the reverse chain rule. The ones we've done so far was pretty easy, and the reason they were easy was every single time we had the trig function on the outside, and then the inside function was algebraic, and the derivative of that inside function was a constant. So it was actually very, very easy and straightforward. We're now going to look at using the reverse chain rule where my inside function, where I have to find the derivative, is not necessarily going to be algebraic. So this does make it quite a bit more complicated, and it does make it much more difficult to spot. So I think the biggest issue here is spotting it. Okay, so with this one, it asks for the integral of cos to the power of 3x sine x dx. Now what you need to notice is you need to notice this right there, according to my reverse chain rule. That looks to be a compound function, and I'm going to rewrite it. Hopefully you can then see it a little bit better. It's cos of x to the power of 3 times sine of x dx. Now hopefully you guys will remember from the previous, not the previous video on trigonometric integration, but from the video on the reverse chain rule, hopefully you guys will remember we're always trying to see if the integral of the inside function, which in this case is a trig function, and that's what make these ones different, is that the inside function is not algebraic. The inside function is in fact a trig function. So if you look at that inside function and you say, I need to have the derivative of that inside function, is this the derivative of the inside function? That's always going to be your question. And then if I take my table of derivatives, I can spot it here quite easily. The derivative of cos of x is minus sine of x. So this currently isn't exactly going to be my derivative, but I can fix it. I can fix it making that sine of x minus sine of x, which is the derivative of the inside function. So let's fix that. So I will say it's cos of x to the power of 3 multiplied by minus sine of x dx, so that this is now the derivative of the inside function, but obviously if I put a minus there, I need to put a minus over there. So now again, according to my reverse chain rule, this is the derivative, so that's a little bit of a mess that was made. When we used the normal chain rule, we made that mess when we found the inside function's derivative. So that's going to disappear. That's going to go back into the Russian doll. I'm not going to see this. That inside function, we're not going to do anything to it. We're not going to touch it. The only thing that we're going to integrate that to the power of 3. And to do that, I bring the minus down, and I say this is going to be cos of x, and I add 1 to that exponent, and then I divide by that. And you can, of course, put the 4 over there, or you can put the 4 over there, but that's my final answer. So please don't complicate it, because remember, the only thing we're integrating when we do reverse chain rule integration is we are only integrating the outside function. So the outside function meaning that to the power of 3. So because the inside function was a trig function, it was kind of tricky to spot. I keep on doing that. Sorry. Apologies. I'm laughing at my own private joke, and yeah, that's just rude. Anyway, I am slowly but surely losing my mind. Well, maybe I've already lost it, but yeah, you get it. Hopefully you do. Okay, so the only tricky part there is going to see if I can find that inside function's derivative. But the actual integration is easy because it's not actually a trig integration per se. It's an algebraic integration where I just take that to the power of 3, add 1, so I make it to the power of 4 divided by 4. Very simple, easy, straightforward. The actual integration, spotting it, is the slightly more difficult part. Okay, so this was exercise 2.1 on page 81. So with this particular one, we again go and we look at it and we say, this seems to be right there. That seems to be my compound function. So if this is my compound function, this needs to now go and be the derivative of that inside function. Now you'll see that the inside function is cosec x. So if I look at my standard derivatives, because remember we're looking for the derivative of the inside function in order to use the reverse chain rule. So if I look at my standard derivatives, I will notice one small little problem. The derivative of cosec x is not just cot x, it's cosec x times cot x. So I need the cosec x and I need the cot x, which can be, I think I copied this one down incorrectly. Where's my textbook? Here we go. I think I definitely copied this one down incorrectly, otherwise it's not going to work. This was number 9. That's strange. No, according to book, this is copied down correctly. Okay, just double check. I think it's probably a typing error. Okay, I'm going to assume it's a typing error, and I'm going to assume this is supposed to be a cot. Otherwise, this one will not work. So, the problem there is that cosec x, the derivative of cosec x is not cot x. The derivative of cosec x is going to be cosec x times cot x with a negative. So that is why I'm actually going to borrow one of those cosec x's. So I'm going to rewrite it like this. I'm going to say it's the integral of cosec x to the power of 3 times minus cosec x times cot x dx. And then obviously, because I put a minus there, I'm going to put a minus over there. And that is just so that I've got my inside function's derivative standing next to it. So now I can go and I can say, this is then the derivative that will disappear. That will go back to that little Russian doll. I will not see it anymore. I keep that inside function exactly the same. I don't touch it. The only thing I'm going to integrate is that to the power of 3. So this is then going to be minus cosec to the power of 4x over 4 plus c. Right, that's it. Like I said, I did change that just to make sure this works out. I will then just go and double check this and hopefully send you like a little message making sure that this was in fact a typing error. But this one works out perfectly, so I'm hoping this is the correct version. Okay, right, next one. Now this one is also in that exercise 2.1 on page 81. And it's an integral that the first time you look at it you go like, this is super complicated, because this could potentially be a compound function, this could potentially be a compound function. But again, I go to my table of derivatives, so I can see which one would work here to give me the inside function and the outside function. So if I look at sec of x there, because we did spot it's sec of x to the power 5, which means this could potentially be a compound function, then I realize that in order to get a derivative to use the reverse chain rule, I need sec of x times tan of x. Now, looking at this, it seems that might not work. But if I manipulate this slightly, like this, and I say this is sec of x to the power 5, whoops, this is obviously not a good day for me to do trig integrals. Looking at all the mistakes I'm making. That's better. Sec of x to the power 5. I can then rewrite this. Now if I rewrite this, hopefully you guys will spot. I can put sine of x over cos of x times then 1 over cos x. And I'm doing it slightly longer way. There is a shorter way to do it, but just so you guys can see. Because obviously sine of x over cos of x times 1 over cos x gives me that sine of x over cos squared x. And the reason I'm writing it like that is because of the following. Sine of x over cos of x is tan of x. And then a lot of you might have forgotten, but 1 over cos x is sec of x. Because sec x is the reciprocal of cos of x, so that's why 1 over cos of x is sec of x. Now the reason I did that specifically is because we've already said that the inside function's derivative, sec of x, using my standard derivative there, is going to be sec of x tan of x, which 100% correct. Remember, the order in which you multiply doesn't matter. So this is then the derivative of that, so this is going to disappear. I'm not going to touch the inside function. I'm just going to find the integral of that outside function. So I'm going to integrate to the power of 5. So that's then going to be sec to the power of 6x over 6 plus c. And I'm done. Okay. Now we do have a couple of combination sums that we need to do. Nothing too serious. I am going to speed it up ever so slightly, just so that the video doesn't get too long. But I think you guys understand understand that the trig integration does take a little while to get through. Now with this one, and the reason I call it a combination sum is quite simple. It starts by saying it's the integral of sine to the power of 3x dx. Now, a couple of issues. This is not a standard integral. I do not have sine cubed x on my table of derivatives. Secondly, I don't have a second function that it's being multiplied by. So currently, I cannot go and use my reverse chain rule as it is. But if I just go and I split that sine cubed x into the following: sine of x times sine squared of x, then I make over here my square identity available for use. It's still not a chain rule. Hopefully you guys can spot it, because the inside's derivative is not sine x. The derivative of sine x is not sine x. But that right there is a square identity. So I can rewrite this saying it's sine of x times 1 minus cos squared x dx. And then if I simplify, I get it's the integral of sine of x minus sine of x times cos squared x dx. I'm just going to put a bracket around this. Now, hopefully you guys are aware of this because we have been using it. We haven't written it out per se, but we can split up this integral because of the minus, and we can say it's the integral of sine x dx minus the integral of sine x times cos x squared dx. So this is available to you should you want to use it. Okay, now suddenly this becomes doable. And the reason it becomes doable is because that sine of x dx is a standard integral, which is going to be minus cos of x. And this one now becomes a reverse chain rule. So this particular one, you can see cos of x, if I find the derivative of cos of x, it's going to give me minus sine of x. I just have to do a quick manipulation there. I can put a plus there and a minus there, because now the derivative of cos x is minus sine of x. So that means this is going to disappear back into that rational. This is going to stay the same. I'm only going to integrate that to the power of 2. So this is going to be cos cubed x over 3 plus c. So add 1 to that 2, make it 3, and then divide by 3. Okay. There's one more like this over here, number 11, and this one is also pretty easy and straightforward. You split that up into cos of x times cos squared of x. So cos squared of x is then going to be 1 minus sine squared of x. And then I've got the integral of cos of x dx minus then cos of x times sine squared x. There you go. So this one, cos of x is a standard integral. The integral of cos of x is sine of x. And then the integral of sine of x, the derivative of sine of x is cos of x. So this one is reverse chain rule, because that sine of x, the derivative is cos of x. So the derivative, that little bit, is going to disappear. All I'm going to do is I'm going to keep that sine x. I'm just going to integrate that to the power of 2, which means it's going to be sine cubed x over 3 plus c. Now, this one was in the IB 2019 paper 1. It's 11.4. I'm not going to do it. I actually want you guys to try it on your own. I will, however, go and on my own, I will do this particular example and I will write down the solution. So if you look at the notes that accompanies this video, you can then go and see it. But I do want you to try and do some of these examples on your own. Thank you very much for listening.